Hybridization in molecular structures. So from the atomic orbitals or Lewis dot structures, we can come up with hybridization molecular structures to help us put in a 3D structure using the valence shell electron pair repulsion theory, Vespert. So if we have sp hybrid orbital, the orbital shape is 50% s, 50% p orbital. So it's a hybrid. It's someplace between s and a p. These molecules that are s and p always have a molecular shape of linear, which means the bond angle is always going to be 180 degrees. So if I have acetylene, and this is hybridization made easy, I want to look at this carbon here. How many high electron density regions? Regions are around that carbon? And the answer is there is only 2 around that carbon. That means it is sp, hybridization. So each one of those bonds is 50% s, 50% p. So what about now this carbon? Still 2 high electron density regions. I guess I should circle them. There's one here, and the triple bond counts as 1 region for 2 regions. So it is also sp3. While we're here, let's just do the hydrogen. How many regions around hydrogen? There is 1, so it is only s. And hydrogen can only have an s orbital because that's all it has, 1s1. So sometimes we can have an sp2, hybridized orbitals. If that's the case, it's going to be 33% s and around 67% p. Let's see. Example. Yeah, we'll go. This is acetone. So I am interested in this carbon. How many I'm looking at for high electron density regions around it. That carbon there's 1, 2, 3 regions. Those 3 regions, the bonds coming off of that carbon, are considered hybridized as sp2. It is known as trigonal planar. And its bond angles are roughly 120 degrees. So what about sp3? They are 25% s and around 75% p in the shape for hybridization. So if we have our formula methane here, how many high electron density regions around the carbon? And the answer is 4. All single bonds. That is tetrahedral. Bond angle is roughly 109.5 degrees. And its hybridization is sp3. And there are others, but mainly for carbon, this is what we're interested in. Let's see. So when we did those line angles, and we didn't show a hydrogen coming off. In reality is one of the hydrogens coming off towards us, and the other one's going back into the board. So then here it's going to be going back into the board and towards us. Oops, I got this one backwards now. I will just leave it that way. And of course this is CH3. This is CH3. So we're trying to follow the line diagram because I forgot to draw it. Because tetrahedral, in theory, is this shape, a three-legged stool with a flagpole, where two of them are in the plane. These two bonds are in the same plane. One's in coming out. One's going back into the board. And that's what I'm trying to show with a line angle diagram. So if we tried another one, well, I'm going to put that there. Put my oxygen in. Well, this is a CH3, so technically there's one coming out here, one going back into the board, and one going up in the same plane. This one here, there's not, so this is an sp2. I should go the other way with it. This carbon here is an sp2, so it's going to be trigonal planar. So when we come to this one, but when we get to this carbon now, it is still sp2 because of the double bond. And just to review, remember, in double bonds, it's always going to have one sigma and one pi bond for double bonds. So if we drew a compound with a double bond, well, what do we know? This is CH3. This one here already has 3 bonds, so this hydrogen's going to come straight off of it, and it's going to be an sp2 hybridized. This one here has a hydrogen, so it's going to come straight down. Hydrogen, it is also an sp2. Here we have a hydrogen. It's going to be coming out towards us, and another one going back into the board. And here again, now we have another CH3. So hybridization, molecular structures, the geometries of the molecule are critical, extremely important when trying to draw Lewis dot structures, and it will help us advance very well in organic chemistry.